in it's recording now. I also go to YouTube. So, well, please now we can go.
So yes, thank you for Prof invited me to this. I'm René. A little bit of background for myself. I did my master's in fitting FFR gravity models onto supernova data. And I enjoy the coding so much, not so much the math part. So I decided to go into cosmological simulations, specifically how galaxies, groups of galaxies, clusters, all of these form through the usage of simulations. And yeah, I was working part of Simba. And then, well, nearing the end of my PhD, Prof. Amore Bebe saw one of the videos that we were creating, and he was like, how does this change under modified gravity? So I got pulled back into modified gravity, and we are busy writing the codes to do cosmological simulations in modified gravity, and that's how I kind of ended up here. But most of this talk will be more on my PhD work, so it's not so much theoretical physics or particle, more just making fun videos of physics. Okay, so let's get started. The group that I'm part of is actually quite large. We have my PhD supervisor, Prof. Loksha. She's with me at Northwest University, and then my two co-supervisors, Prof. B, at Edinburgh University and Prof. Arefabo at University of Victoria, Canada. Everyone else, different times I worked with them. Notably, Wagon, we have if there's one person that knows a lot about code debugging, it's like, well, if you have a code, it's about asking. And then more recently, Prof. Amore, he became my postdoc host, and we are working with Sean since he gave us access to supercomputer where we can run these new simulations. Yeah. With that comes a lot of affiliations that we have been part of over the year due to everyone joining up. And I have to give special thanks to Flatiron Institute in New York. They are hosting the simulation, which is around 80 terabytes with all of the data. So I'm just hosting anyway. Okay. So just a quick overview of what we are going to talk. We are going to look at what we mean by simulating a universe, specifically in the Simba simulation, which I am part of this collaboration, and in some properties and how it led to where my postdoc is currently located. Now, so we all have seen Planck's table. It's very good. CMB, they did a lot for cosmology. But if we actually just look up at the sky, this is not what we see. Yeah, you can see with an radio telescope this, but if we look, we see it more something in this region. So objects that form from this initial perturbations from the CMB, yeah, stars, black holes, galaxies, all of these. And when we look at it, we kind of see a snapshot in time. So the question becomes, how did we go from there to here? And the straight answer, we can have a model trying to show us, but we don't actually know. Unless we have two objects that are perfectly the same properties, except one is a bit younger than the other one, and we can infer, okay, this will turn into this. We don't really have that full set of how the stuff that we look at, the objects, how they evolve over time. Now, then people like the Millennium Simulation came and gave us these nice big simulations that show us interesting ways how the energy gets put over into mass, matter, and then due to gravity, they start collapsing and you start forming your galaxies around these connection points. Famous cosmic web, that was 2004, millennium, I'm not sure that everyone this, but after that, there was, okay, the millennium simulation only took dark matter into account. What about ironic? So over the years, as computational power increased, we started adding ironic. First up was Eagle simulation. About a year later, the similar simulation came out. Eagle is from Leiden University, similar at Edinburgh University. Well, it actually started back in South Africa. Prof. Devi was busy there when he got there. And then Illustrious ENG from the US. And these are some of the big three. Others have come along over the years looking at different properties. But we can make this simulation where we see how particles interact with each other for a bit of the universe. But what actually goes into these simulations? Well, your first ingredient needs to be cosmology. If you want to create a universe, you kind of need to know the physics behind drugs. So for now, all of these big simulations take into account lambda CM, but we only start from the CM bigger numbers. Kind of say we assume the particle physicists, they knew what happened there, and we assume they had fine. Simulations like Ramsey's from David Mota and their group, they have looked at dark matter only simulations where they change the cosmology, but doing it on the Baronic scales becomes infinitely more computational. And the reason is the actions that happen inside. It's not just the cosmology, it's how the particles interact themselves. So the second one would be, well, formation of particles. Yeah, I'm not doing it. You're responsible. We kind of assume all of this are correct and then just take the particles as they are from predictions or theory based. And then we give the correct Big Bang nucleosynthesis, the primordial elements, the quantities of how much baryons compared to dark matter, all of that, and the distribution. Okay, now we know we had the CMB energy, we have the particles, we can change it from the one to the other one. But now we also need particle interactions. This is the Clifford Nebula, and these gas clouds. So as the universe expands, the gas goes down, and now they can start forming stars. But so while they are in this just stable, it does not form stars. Now we get shock waves or anything pushing this gas clouds above the critical G's mass, and they start to collapse to form protostars, and then so on. So these particles need to be able to recognize each other, not just with gravity, but also how can they interact with each other to form new types of organisms. So they need to be able to go from gas to stars in the simulation. If we have stars, now we need to start taking into account stellar evolution models. And so we all know that stars, like humans, have a birthday, and then they spend their time at work, then it's old age home, and then they die. But unlike us, they go out with a big explosion in most cases. Even novas aren't that small, but different types of events happen at the end of a star's life. It can be very boring with ending just with a wide open planetary nebula or even in black holes. Okay, so now we need to know how to change stars with black holes in the simulation and how black holes now interact with everything else. Okay, so we need that physics. But black holes start becoming they got these big tools that grab the gas from outside, and then they start creating these disks, which a lot of us, especially the supermassive ones, start creating your galaxies. But inside here, there are a lot of pressures going on. Heat rises, pressure rises, and eventually we get HA. Okay, so now we need to take HA. And that's what we mean. Adding these things when we added baryons, just the simple idea of adding baryons, even though it's just 5%, it keeps adding to what the simulation needs to be. Okay, but now jets. So we now have a jet. The jets are very energetic, and they reheat the gas around it, the cluster medium. But you need cooling gas to make stars. So you're kind of blocking out star formation when these jets go off. And then as time goes on, the hot gas moves and they start falling back due to gravity. But by this time, they start cooling again and you form new stars. So it's this interactive loop between energetic feedback systems and how it gets back to forming stars. So there you switch off stars, there you switch it back on, the formation. And again, the simulation needs patency. Yeah. Okay. But supernova are also feedback systems. Does this same principle count? Yeah, just smaller scale than these big jets. But more importantly, our elements get formed from that. So our simulation does not just stop at hydrogen. It needs to go to form all types of chemical elements. We consist out of different elements. So the simulation also needs to do that. And the problem is different types of stellar feedback events results in different elements being formed. Type of star, type of supernova, different type of element. And then they also occur on different time scales. So, okay, get me better. Now, luckily for us, Prof. Shaki Kobayashi, she went and did models on this for most of the big elements, where you have the beginning of time and how that element accumulates based on each type of stellar feedback. Okay, so you have your Big Bang nucleosynthesis, the ones right after Big Bang, and then different types of supernova type 2, supernova type 1A, AGB. Okay, so we know how this works. Can we go on? We can add molecules, but I don't know a lot about chemistry. We can even go further, we can add biology, but then questions of life are longer 18. So as a physicist, we kind of stop here. And where we stop here depends on which elements the simulation is important. Okay, so SIMBA is one of these simulations that has all of these ingredients that take them all into account. Yeah, they have some assumptions. That's why I had a PhD. But yeah, SIMBA has two components: gizmo, which controls the beats, the gravity, the particle interactions. This is simulation 1. And then it has SIMBA, its own subgrid packages that controls how stars are formed, how black holes are formed, their interactions with them, chemical evolution, these types of things. And this happens on sub-resolutions. By that, you mean you add your numerical methods, this would become a new star and then interact with its surrounding. So everything that SIMBA calculates will be within one pixel. You don't have tons of pixels, how the star forms. Everything's right. So your normal numerical methods of interaction and information needs to be approximated to a single cell, not using numerical analysis. Now, gizmo being, there were a lot of smart people, how they wrote it. So second year in numerical analysis, not so much. Their cells can change shape based on the interactions around it. So it's not just forward, back, down. these cells shift. And if you allow them to have these interaction-based changes, it naturally collapses to form these groups. And that is kind of how we form our galaxies with the correct interaction. Okay. However, all of these simulations, a lot of assumptions. They take a lot of computational power. So, yeah, for instance, Simba only has 11 elements. We have a lot more than 11. But these 11 account for 99% of all elements, abundance that we can see in the universe. So 1%, I feel it's not that bad. More importantly, that's a big one, is the instantaneous recycling of distributed metals. Basically, the moment a star is formed in the simulation, the computer calculates what metals or elements that star will create throughout its entire lifetime, including its supernova death, right from the start. And then rather than waiting until the end, we kind of like, okay, I know what you are going to create. Let's just distribute it instantly. So the moment the star is born, everything it will ever do, it's just given. It's equivalent of somebody coming to watch your baby and like, your baby is going to win the Olympics. Here's your Olympic medal already. That's kind of what the simulation does. It's not a very good assumption, but surprisingly, it does work actually quite well if you compare it to observations. Another one that's quite, it's not really a good assumption is delayed feedback. If a star in the simulation is smaller than a set amount, arbitrarily set, it will be assumed that this is a star that will go supernova type 1A and instantly go supernova type 1. And if it's larger than that, it will stay on and live forever and be an HEB star forever. There's no in between of evolution, I guess. That's from the static side of abstraction. If a star is deemed to go supernova type 2, it just like automatically 18% just go. No conservation of energy or mass or anything. It's just like we kick out 18% of the star, then that was our supernova type 2. These are, they work and they produce realistic looking galaxies. They are not realistic themselves. So this is what my PhD was based on. We wanted to try and get rid of some of these assumptions while keeping the accuracy that some had. So we used Prof. Kobayashi's chemistry model, which she already showed she knew I great. And more importantly, this one. Treat star particles as evolving stellar populations. So they, like we said earlier with these, this one, it treats them through this stage to calculate the correct amount of each element that needs to be created. She also is also addition of new types of stellar feedback. Super engineers, hypernovae, and failed supernovae. These are stars that started going supernovae, but the black hole it formed was almost too quick and it just pulled back everything into it. Now, if you combine these two, King 5, Simba, you get my project, Simba C. I had some implementation stuff that we had to figure out to get instantly work and get rid of some of the assumptions. Interesting ones, the wind scaling velocity. This is just a number that were given to how fast winds can move in the simulation. And this had to be lowered due to the new feedback. And it actually now matches observations. Where previously it was almost double the speed from observations to get realistic type of that. It's interesting. Yes, the video from our simulation. Basically, we in this video we have our energy distributed. This is not, it's after the CMB, but before the stars start forming in the simulation. And so the energy will cool down, and we are watching the formation of a cluster. But the universe is expanding past the camera in this case. Okay. So yeah, you'll see that. So the first clumps or groups of stars and small galaxies started forming along these webs, and now you'll see the formation of a group here and a group there. And then after that, so there you have your galaxy groups, how they merge in the pool in the galaxy and gases around it. And now due to gravity, they will start merging. Okay. Now, as they merge, you'll see merging shocks arise. We don't code in the merging shocks. That's just energy released from these particle interactions. We build in how fast they can move out with the wind velocity, but we don't actually go in how that it must be the set amount you need to stick these shock waves out. Similarly, as we were playing around with the data, we actually found one of the galaxies. Now, their simulation has about 400,000 galaxies that form. And we actually found a nice looking spiral galaxy. And just for interest sake, how it formed, basically, so at the end of the energy, we centered it around its supermassive black. Right after the supermassive black hole formed, and then how it was in. Now, this is much deeper into the simulation, so much less particles. But yeah, you can see the gravity pulling in. And then it starts from
Why isn't it
I don't know.
probably people are not watching it? I'm just maybe you're not on the Zoom sharing the same.
Yeah, okay. Let me stop sharing this. And let me just share my window.
Yeah.
Okay, thank you. So you can see this, and you can actually see energy being released from the same mass black hole. And again, we don't actually code this. We just put the physics and allow the simulation to choose what fits, which thresholds are being met. So yeah, it is actually quite good. Jim's guy at Lashes, you were like, he said he's been working on these simulations for so long, and it still amazes me that it actually forms galaxies just out of nothing, basically. So it means our physics, at least on some ways, fine, even though we have a lot of big assumptions. So interesting results that we got. We looked at how our stellar mass is distributed in the different galaxies. We have observations that we can compare to, and we can see somewhere it's actually getting, especially in the middle, the intermediate mass galaxies, kind of like okay, not too much should be yeah. We are actually producing the correct amount of stars and the correct masses for those stars in these galaxies. We looked at properties like quenching and star forming. And here you can see, so the lines of the dots are observations. And for instance, overproducing massive quench galaxies, but we are moving better than the previous version of the simulation. And for small star forming galaxies, again, we are actually quite a lot better than the dash line down there. So even the makeup of our individual galaxies do tend to align more with what we are seeing in observations. Okay, we looked at the black holes. This the previous summer simulations were able to produce realistic black holes in a sense, but we couldn't do the previous simulation couldn't do smaller black holes, which we now can. And if you compare to the observations, our black holes are being created at again the correct masses, correct rates in the correct galaxies, which are quite interesting. Now, this is to show how good that bad assumptions was. This is the metals that were created inside the two simulations. And for Simba C for blue, and you can only see, it doesn't matter at which redshift, Simba actually gave the correct metals. When we first ran Simba C, we actually were underproducing the metals. It was running about, and it turned out that due to the latest versions of the yield tables from observation, Gen 5 is set up to actually produce less metals from the start. But now, if you have less metals, your next gen stars are born incorrect, therefore leading to less black holes, leading to less feedback. So it was messing up that loop. And to solve that, we had to change that weed scaling at the start. So to get back to the observations of Nicholas. But now it's interesting. The blue one, is more accurate, more realistic, but we still managed to get the previous version of Simba with the correct methods. So the question is, how many other assumptions or in simulation that is bad assumptions, but they just kind of end up giving the correct answer anyways? It's a difficult question which we don't know. Like, it's a big mash of different physics laws, and we don't know exactly always which one is the correct answer for which property that we see. Anyways, going on, we looked at individual elements, and so first of all, Simba out there, it's completely wrong. And that was due to it not really taking the different feedback models into account. The blue in this case is observations. And then the black is Simba C as every single week at all source in the simulation. And we actually getting, if you look at individual ones, we are getting close to what observations are saying. And this is actually a very important one. It's a known trend in observations from the 60s, where this is due to the time delay between supernova type 2 and type 1A when they start forming. So you can track that time delay with this. So the fact that we are getting it proves that the new method of actually evolving stars and putting that time delay in actually means the reduction of the elements in the simulation. From this, we started, what can we actually do with this image? Like, can we have it now? And there's a lot of things that we can do. So we decided on X-rays. And at first, we just built the basic idea of a circle around the cluster, measure the energy coming from that loop or cluster, convert it to X-rays, and now we have our luminosity, stuff like that. So X-ray properties in different bandwidths. So here we had two other simulations that did not take into account all of the physics. First one had no feedback. Second one at least had stellar feedback, but no. Okay, but interestingly, compared to observations, Simba C, the new one, actually does a lot better. But why was Simba in pointer, not Simba C? Why was it so low? It was very dim compared to Simba C. We did not change the feedback in itself. And it turned out to be actually due to entropy. So the feedback strength that now was lowered due to the wind velocities actually meant that we had less chaos going on inside. So the entropy got lowered for Simba, and that has an indirect play with the luminosity, the X-ray luminosity. It was interesting, and we actually get quite nice results. Okay, since we're looking at working with the chemistry update, we would again do this, and this was an interesting result. At first, we did not know how to explain it. If you look at this, ignore the large animals. Simba and Simba C were producing the same amount of silicon to iron, but not silicon to oxygen, meaning that we were producing more, more silicon and iron relative to oxygen. And we were like, okay, but why is this? It ended up being due to the additional failed supernova. That oxygen that would have been released in all the models would have been counted extra. Now it's not being released anymore because it falls back into the black hole, and you end up with this this reality coming from. Just interesting that we found it. Okay, but what if we can go a step further? Not just look at the energies in the galaxies. What if we can take a space telescope and put it into our simulation? And that's what we are trying. So this paper has not been released yet, but basically we are using the Athena detector. This telescope has not been launched yet. It's, I think, slated for 2030 or something like that. We did use Chandra, but Chandra is very low resolution compared to the detector that's being built for Athena. And then we put it into our simulation and we point it towards our object, and we take the energy, we assume a absorption emission model, and then convolve that into the detectors, the detector, and then we can actually start extracting emission lines, absorption from this. And this was an actual cluster in the simulation, and that much change coming out of it. And yeah, we managed to actually get. However, this particular graph is a bit outdated. After that, we started updating this file, not just the basic idea of conformity, but making it more consistent to what our real observations would be done. First, we had to isolate the R5 feature, the full one. This was basically due to the fact that when we put in the telescope the first time, it was always at exactly the same distance. So if the cluster is big, you only take measure the center. And if it was a small one, you get the entire center. So we are very different types of events. So we had to make sure that our entire region is in. We had to remove the BCG and GG from the center, since they have very active regions that could mess up the statistics from it. In real astronomy, they also have to do it, but it's much more complex way. We can literally, there you are, take you out, since we have the data. We had to update Athena, and we are hoping to keep updating it as they affect the detector for it. And then we started introducing mosaics so that you can get up much more close and take much more photos while keeping within the full region of cluster. We also started binning the photons together, X-ray photons, to ensure that our distance are better and not moved to one side due to photons that is out by us. With that, we can also do model fitting with NCNCs, tracking each individual element, and then we can start producing plots like these, where we have abundance. We have been we are in the process of gathering observations. Some of them green and black in this case is observations. Now the blue is simulated groups, red is simulated clusters. And we can see we do get similar things to a certain point, but considering we have a big simulation without ever taking this account, we actually get close answers. Actually, quite nice. So what we are going to go on now is complete this, make the full catalog of all of these data sets. Simba-C needs to be incorporated with Swimba, which is Simba plus Swift. They are updating the now, as far as I know, this has been completed by the group in Edinburgh, but they are busy calibrating this. Simba-C also needs to go into IDNAS and the other project which is Zoom simulation, specifically looking at like one cluster, one galaxy and how they evolve with that or change or something. And then do similar things for radio that we did for X-rays. This is a student from Edinburgh, and we also students that was in the camp. And for my own work going on with this, we got to get to this. So this was the video that I created, the first one that I created, feels so good again. And it's a basic 2D projection. We do that. We start again quite early. And we are keeping this so you can see the scale grows with the expansion. And to stars form, they start grouping up and it formed this nice cosmic wave. And then this was the Prof. Baby saw and it's like, how does the cosmic wave change with modified gravity? And I said, I did not know. And this is more recent. We learned how to do it in 3D. So you have your images again elapsing. We do the yellow in this case is star particle region, so kind of the size of dwarf galaxies that are star forming. And and even see some of the smaller galaxies being ejected. Okay, so now getting back to the question at hand. If we can identify these filaments, it's easy to see, but telling a computer how to recognize the pattern is a bit more difficult. We can see how the properties changes with distance from these filaments. Now, these can include under the questions how does the filaments themselves change? They're more diffuse. They stay the same. If it's a good modified theory, they should theoretically stay the same. Becoming more diffuse, more constricted maybe. But the second one is kind of where we are going, and that's the variance. Now, like I said, the Valencia group with David Montale, they kind of looked at the first question they using dark matter. But a galaxy that's inside these filaments, a galaxy outside these filaments, showing different properties due to their environment. So if your filament gets changed under the gravity, how does the galaxies within it, do they become more realistic? They're bad. How does their properties impact by their location in a modified universe? And then my own student is currently working on this idea. We take the power spectrum from the CND, the emission conditions, and we start modifying. So at this stage, he's looking at changing the dark matter content. So giving more dark matter, less dark matter, putting it into the simulation. So our expected to be with more dark matter, you'd have much bigger potential wells, so much more localized clusters forming and much less and bigger voids. Whereas with a smaller dot matter content, we assume it could be much more distributed than what has been for its form. Stuff like that. So you're going to look at things how to change that. Yeah, that's
Thank you so much for your talk. It's time for questions or comments. Not many.
okay.
Okay, so the first one is you're showing simulations on macro scales, but at some point you showed also the formation of a galaxy. So, what is the real resolution of your?
So for us, you can get down to a realistic galaxy. What we would at that stage we would say, okay, the galaxy properties become realistic, and times 10 to the power 9 solar masses. So a bit smaller than Milky Way galaxies, but larger than dwarfs. That said, we have more recently released a symmetry high resolution, which should be able to resolve dwarf galaxies on the scale, but they reduce some of the peaks. So we could only simulate it up to, I think it was 50 megaparsec, whereas the main one, so it's 50 megaparsec by 50 by 50, whereas the big simulation is under bound. So it's about a factor of 8 that we lost due to being able to go to the dwarf regime. For the other big simulations, Eagle has better resolution. They 2 times 10 to the power 6. So they would fully be able to resolve dwarfs. However, they are also smaller even than us. Illustrious does not have such high resolution. They make it big, so they can do a simulation. They are busy with a gigaparsec by gigaparsec. That will have millions of galaxies produced in them. Like the base, I think, Illustrious TNG 300 that was times 10 to the power 10. So basically your intermediate galaxies going up. But these numbers are, they are exact numbers you can get for these. But yeah, it's mostly in the range of either high dwarfs going into the low mass galaxies and up. If you do want to get higher resolution, you can do something like fire. A lot of Simba's code is actually based on fire. And they can do, I think they do one galaxy, simulate just the one, kind of like how INAS and the project, just one cluster. And I think I heard something about they can get down to times 10 to the power 4 solar masses. So they can get quite nice dynamics within a individual galaxy. So Simba just kind of like, well, you guys already figured out how to make the one grid sound thing. So we just get to take your physics, put it inside. So based on their assumption that their galaxies are realistic, we assume that what's happening in our one cell is good.
Yeah, so what kind of computing system do you use for running this simulation?
So the main simulation we did, most of the time I've been using my Gara supercomputer in Canada. Profile Room has a very big grant that all of his students can basically use my Gara for as much as they want. There is some limits, but I think we have only once actually ran out. But the big simulation was run on Flatiron Institute's own supercomputer, so it was not a government one. And it took about 3,000 cores running for 3 months. Yes, so that's why Modify Growth haven't really been introduced into these simulations. They are just computationally very expensive. And so it's hard to actually get time for it, but yeah, that's okay. Give flat iron the credit. They did it for free for me, so okay. And then more recently now with the addition of Sean, he works at the CHBC in South Africa, and they have allowed us, as long as we don't do 100 blocks, but a 50 blocks, so for 1,500 cores running for 2-3 weeks. That they were like, okay, you can do this and run field simulations.
Simulation.
Have a general question. In this kind of simulations, you can see the different epoch of universe being the matter combination or combinations, how the galaxies or cluster change and their evolutions.
So yes, in a sense, we can't see the radiation dominator that happens before our simulation even starts. Matter dominating going into dark energy, we can technically track that. We have the data. You will have to go fish out the info out of the data, but we can technically do it. But we haven't really, as far as I know, looked too much into outer dark energy effects stuff. That's still kind of, most of these things are, let's just get the matter part correct.
And how I cannot imagine how this code, this might be a huge code, how this structure, but is it possible somehow to to change the general relativity dynamics by some of the gravity?
So that is what we are busy at. I can quickly show. So the easiest way, there is different ways. Gizmo actually does have built-in functions where you have self-interacting dark matter. They have basic modified stuff, but in most cases, they say if you do want to modify the cosmology or the gravity, you need to do basically, so you set up a table. So this is where we are currently. At different redshifts, you take your model to at different redshifts, you can change your gravitational constant if you want to be not a constant but change with time, and then your bubble. You can change that. Gravity itself become a bit more difficult, but on the system they show you every single thing you can change. It's how daily system works. So gravity would be so you can go what precision you want, how they must release. And so there are a lot of things that you can adjust. Changing the code, adding your own type of way, that's a bit more, just more, this document is always okay. I know, so you have self-interacting document. It's fun. Yeah, you have local screening, gravity effects, you have self-interacting document. And they do like, hey, here's the code you can change. Just if but how you build it in comes difficult. Just for me changing the already built in supernovae took me a PhD. So yeah, people have been working on these codes for a very long time.
Okay, so any other questions or comments? Maybe online, anybody? If not, then let's thank Rennie again. Now, Okay, we are almost there.
Patience.
Yes. Yes. This even the I organics. It's safe share the screen. Okay, the you need to share the screen, else we see the video. Okay, very well. So now we are ready to continue. And our next speaker is a special invited guest from Chile. He's Fabián Elises. He's coming from the and he's going to tell us about static solutions, right, in gravitation. Please, go ahead.
First of all, thank you, Gonzalo, for inviting me here to this nice city. So far, I have enjoyed a lot city. I didn't know that it was so hot for coming by bicycle, but here I am, finally did it. So thanks a lot. So as maybe you may guess, these kind of solutions are exotic solutions that you can find in modified theories of gravity. These are the so-called stealth solution. I will explain you what is this about. And this is a work in collaboration with some friends, with Guajardo and Cristiansen Lara. And so before entering into details, I should start talking about modified theories of gravity. We already know that in modified theories of gravity, there are strong motivation to implement or to find some corrections to GR in order to give some explanation for some open problems in GR. We know the Hubble 5 sigma Hubble tension problem, the coincidence problem, the cosmological constant problem. We know as well that when we need to provide a modification to GR in the strong gravity regime, since the string theory at least predicts that in the low energy limit, we will have some correction. To my surprise here, in Spain, there is a quite strong group in modifications of general relativity by higher order correction. We have found that higher order corrections in the curve can kill the singularity problem as a quite nice modification of GR. Other modification of GR, which is quite simple, is with the scarf. Modify GR with scarf. But here we have to take care of, to mind the no-hair conjecture. No-hair conjecture prevents to obtain black hole solution. This means that black hole solutions cannot be described by other conserved quantities other than the mass, the angular momentum, and the electric charge. So if you want to provide some other energy matters, other fields, then this conjecture tells you that this is not compatible with a black hole solution. So the people start working on finding ways how to circumvent the no-hair conjecture. And the typical example is this one that appeared like 50 years ago and found independently by two different groups. And this managed to circumvent the no-hair conjecture by a non-minimal coupling between gravity and the scarf. Then what happened that Hordensky theory by that time was already, people was aware about Kordensky theory during that time, but they forgot it soon, quite soon. But then what happened that was rediscovered by a limit from the Galilean theory. People started working on other kind of theories, and they found that there was some kind of relation between Galilean theories and Kordensky theory. This resurfaced the attention of the community, and the community again started working in Katie black hole solutions. Why? Because Kordensky theory is the most general scalar tensor theory that provides second-order field equations for the scalar field and for the net. So the people exploit significantly the scenario of Kordensky theory and even beyond, and now they are working in the degenerate higher order scalar tensor, the dosed theories. So there are many ways to circumvent the no-here theory. There are no-here theorems even in Kordensky and beyond Kordensky, the seminal work from Lu and Wee, which states that the black hole solution cannot be compatible with regular scalar fields with regular currents. So now we have to remember that Willis told us this quite celebrated phrase that space-time tells matter how to move and matter tells space-time how to curve. This is something that you expect anytime that you modify with some matter field, you modify gravity. So you expect that other non-trivial matter fields will backreact. How is this related with the stealth configuration? The stealth configuration are particular kind of solutions which are non-trivial matter, but at the same time no back reaction. You can find no back reaction. So this somehow defines this Wheeler paradox. So imagine you have your favorite theory with some effective stress energy tensor. You compute the T mu, and this T mu is equal to 0. This is something that can be seen in more detail, for example, in a scalar tensor theories. A scalar tensor theories, this is the action. We identify two fields, the metric and the scalar field. And let's split the action in two parts, a purely metric part, which is the one red, and the scalar tensor part, which is composed by the metric and the scalar. So, in order to find stealth configuration, we will consider the Einstein field equation, the left-hand side given by this guy here, and the right-hand side given by the effective stress energy tensor of our theory. So, in order to find this stealth scalar field, we have to fulfill the stealth conditions. T mu has to be 0. What is a typical example? The most simple example I can. This is purely R, okay, the purely metric part. And this is a non-minimally coupled scalar field with some potential. So the procedure here is to take the metric, the flat metric, and then to plug it in the T mu, and let's see, and let's pray for a non-trivial scalar field. Let's see what happens. They found that, in fact, there is a non-trivial scalar field with this form. These are the coordinates. So the coordinates of the base part. And this is supported by this power law for the potential, for the self-interactive potential. This has been found like 20 years ago, and this was dubbed as the gravitational Chichester effect because it resembles what happened with this with the Chichester cat smile. When he disappeared, there was something reminding me was his smile. So this is analog with the fact that once you switch off gravity and you consider flat space-time, there is a footprint given by a non-trivial scalar field, which is a manifestation of the non-minimal coupling between gravity and the scalar. So that's why it was done like this. Okay, so this was the first stealth solution, and then the people were crazy trying to find more stealth configuration in different theories. You can see here that the first four for results for a stealth scalar field, but even basically the same group in different contexts with stealth, overflying, Minkowski, BTZ black hole in 3 dimensions, and even cosmological scenarios. Then, when the people focus on Kordensky again, they found with some other stealth scalar field in 4 dimensions with other black holes like Schwarzschild ABS, Schwarzschild inner rotating solution scale in those gravities, and also out of scalar tensor theories with more exotic actions principle, like in new massive gravity, vector Galilean theories, hypergravity, nonlinear electrodynamics, etc., etc., etc. So, as I mentioned, for the archetypical example that I described before, there is a standard procedure. The standard procedure is to first solve the left-hand side of your equation that comes from the purely metric part, and you will find a solution. So let's suppose the solution is Minkowski, for example. Then you take Minkowski, you plug it in your TNU, your stress energy tensor, and then you want to find a non-trivial scalar, non-constant scalar. So this is what we call the standard procedure or A to B method. What we will propose, the reverse procedure, we will start from the stealth condition and we will restrict the space-time geometry only by the stealth conditions. And finally, we will find some candidates like purely metric theories whose quantum solution can match the geometries restricted by the stealth condition. This is the last part. So this is what we call B2A method or reverse procedure. So this is quite generic procedure. It's a different approach to find stealth configurations. So we need to apply this reverse procedure to something concrete, to some kind of a particular scalar tensor path. Of course, our favorite one is this one, the RP square. Why? Because it has proved to be quite successful finding black hole solutions and in stealth solutions. In all these articles, they have found different stealth configuration with the other or not, but all of them has in common that contains this RP square term. Even by accident, in this one with star, this by fine tuning, they found black hole solution, and then in the space of parameters, they found that by fine tuning the parameters, they can banish the TMU, the stress energy density. What they have called this solution in common? This is one of the questions that motivate these results. Can we collect all these solutions and put them all in some theoretical framework, some generic theoretical framework? And then, once we have full control on all these solutions, can we survey for some other imprints from these gravitationally undetectable solutions? So these are the questions that motivates this. What are the remarkable aspects of this procedure is that the geometry, as I said, is only fixed by the stress energy condition, and also it allows to broaden the landscape of scalar tensor theories with stealth configuration. So the outline of this talk is as follows. First, I will show you briefly how to apply the reverse procedure to the non-minimal coupling, RP square, and then we will see what are the possible geometries given by the stealth condition. Then, of course, we want to apply the reverse procedure in order to recover or to find new solutions in modified theories of gravity and scalar tensor theories. So first, we will recover solutions in GR, and then we will go beyond GR, and we'll show that, in fact, we can find some generalizations of previously found solutions. Finally, we will search for thermodynamic signatures. So as I mentioned before, these are gravitationally undetectable matter fields, and we will search for some thermodynamic signals. We will see that, in fact, we can detect the stealth scalar field through its thermodynamics. So we will focus in this skeletal subpart, the non-minimal coupling between gravity and a scalar field. We will have a self-interactive potential, and of course, the kinetic time. For simplicity, we will consider a static d-dimensional spacetime with a base manifold given by constant curvature. So it can be isomorphic to the sphere, to the flat space, or to the upper body. This is a quite compact way to write the base manifold given by spanned by these x coordinates. This is the stress energy momentum tensor, and as I mentioned, we are interested on solving the stealth condition. So for that, we redefine the scalar field. We can write the T mu in this way, and we will post that this T mu has to be 0. And this, the nice thing from this equation is that you can separate variables and write this variable as in this quite nice way. You can find the most generic solution for the stealth condition given by this generic scalar. Then finally, what we have to do just to come back to the initial definition of the scalar. I will not bore you with all the technical details of how to solve it, but I will just give you the result of this. The moral after solving all the differential equations is that you have two branches, the time-independent scalar field and the time-dependent scalar. So these are the results. So the stealth conditions restrict the geometry for the metric function in this way. So for example, in d equals 4 or higher dimensions, the purely radial scalar field, that explicit shape of this scalar field, I will give you in the next slides. But the important thing is that the geometry is restricted by the rigid black hole here. For example, the spatially dependent scalar field is given by this exotic power law here. And the time-dependent scalar field by this, which is restricted to be only asymptotically ADS. The potential in general can be written as power law here. Keep in mind that this C coupling is the coupling constant, C parameter here. So the moral here is that any gravity theory whose vacuum solution fits in these geometries admits a non-minimally coupled stealth scalar field. So now we will recover with this procedure some previously found solutions. If we pick up the three-dimensional time-dependent branch for the case of Einstein-Hill interaction with cosmological constant, and of course the non-minimal coupling here, we find that this solution here is compatible with the BTZ black. So this is a stealth solution overflying the BTZ black. These conditions here, of course, are compatibility conditions that allows you to plug this non-minimal coupling with the BTZ. So in principle, from the stealth condition A, B, and C are finally, if you want to match it with the BTZ black hole, you find, for example, that A is related with the cosmological constant. In higher dimensions, it's the same story, but this solution is more generic than the previously found. And this recovered the seminal work from the Mexican group and recovers so the steel solution overflying a flat space. As a result of this procedure, we extend the solution for the ABS space. So far we have restricted ourselves only to the Einstein-Hill interaction as the purely metric path. Can we go beyond? The answer is yes. Now we can, for example, choose the new massive gravity in 3 dimensions and see what happened for the stealth configuration. So we using this matching, these compatibility conditions, and using the time-dependent branch from the stealth condition, we found a novel time-dependent stealth solution for new massive gravity, non-minimally coupled to the scalar. In fact, this recovered the static solution found previously by Hassan et al. If you switch off this constant here. And we can continue generating more and more solutions. For example, the conformal in four-dimensional conformal gravity, we can plug again the nominal coupling, and this is the result which is compatible with the Rieger plug. And it takes this quite nice form for the integration constant A, B, and C. We can do this for log gravity as well. We can have the full power of the log invariants, and you plug the scalar tensor part. These are the compatibility conditions, and finally, this is the most generic stealth solution with this scalar field. So remember that these x here are the coordinates of the organized manifold. So it depends not only the radial, also the base manifold. So again, this is a novel spatially coordinate dependent stealth solution. In fact, we can recover all the previous work found in the literature in the planar case, in the Gauss-Bonnet and log gravity by choosing the purely radial parameter. So this is somehow a new solution or an extension to the topological black holes that they found in log gravity. Now the question that now that we have all these different solutions, the question that arises, we can find some physical impedance on the solution. And for that, we have to choose the most simple solution, black hole, of course. And this is one of the most simple that we have found. And we will study the thermodynamical signature of this. The ancient scalar Gauss-Bonnet, 5-dimensional in 5 dimensions. Of course, in the Chern-Simons point, we have this BTZ-like black hole with this quite simple form of the scalar field. The base manifold is planar, and we want to compute the mass, the entropy, etc. So from the Euclidean approach, the starting point is the meaning over space. So we will restrict to this meaning over space, and we will plug this in the action, and we can write the action as a linear combination of constraints. This is the Hamiltonian constraint. This is the N, the last function that appears here, and this is supplemented, of course, by a boundary term here, which is allowed to have a well-posed variational. As you may know, this is the Euclidean continuation of our space-time geometry, and then the Euclidean time is periodic and is related with the temperature. Sigma is the base manifold, so this guy appears there. So from the seminal work from Gibbons and Hawking, we know that the action can be related with the free energy. So this is a well-known result that established a relation between the partition function and the Euclidean path integral around the classical action in the saddle point approximation. So if we want to evaluate the action, we need to find these guys, the boundary term at infinity and at horizon. But our starting point is this one, this monster here. So to integrate this monster here and evaluate at horizon is quite easy. And you can see here that the entropy is appearing. But at infinity, it's not trivial at all. At infinity, the delta B, the variation of the boundary term at infinity, takes this strange form here. And this is not necessarily a closed one form, meaning that it's not necessarily integral. So we need to find integrability conditions in order to evaluate the boundary term at infinity. One way to do this is to use the Poincare lemma and then extract what is the condition in order to be able to integrate. We have 3 boundary conditions that are compatible with integrability. The first one is boring because it switches off the scalar field. This is what we don't want. The second one implies a rigid scalar field, meaning that the amplitude of the scalar field is frozen, delta phi 0. And the third one is the most interesting because it proposes a secondary head. So the amplitude of the scalar field, the integration constant present in the scalar field, is related with the integration constant of the space and the metric function. Once we consider this, we can integrate the boundary term at infinity, at horizon, we evaluate the action, and with the action, we have the free energy. Through the standard thermodynamical relation between the free energy and the mass and the entropy, we can easily find this calligraphic M, which is the mass, and the calligraphic S, which is the entropy. You see here, this is 1/4 of the area with the effective gravitational Newton constant, which is this d hat depends on the scalar field apparatus. The important thing here is the mass is shifted by this delta M guy here, which is given by this integral. Of course, that we can solve this integral because the integrability condition. So there are two contributions for the mass. The mass that comes when the scalar field is switched off, which is this guy here, and the mass that comes when you switch on the scalar field, the stealth configuration, which is this delta M here. And we can compute it for the boundary condition that I mentioned before. For the rigid scalar field, for example, the mass takes this form. For a function of the amplitude of the scalar field and the integration constant M, a linear function, we take this form, and you already may anticipate what is going on here. The mass of the vacuum solution without the scalar field is screened by the stealth configuration with this guy here that depends on the scalar. And you can take this to the extreme and to totally screen the mass of the black hole and to have vanishing mass black hole, which is why this is quite exotic, but this is not something new. It has found in the literature zero mass black hole with some Lifshitz asymptotics and also in some Lovelock theories. So this is not something new, but it's at least exotic. The moral here is that if you ask yourself if you can detect, theoretically, you can detect the stealth configuration, the answer is yes, because the mass of the black hole solution. So, in order to finish some final comments, the reverse approach is a novel method to obtain a stealth solution, which proposes to invest the usual procedure in finding a stealth solution. The advantage is that the geometry is only restricted by the stealth condition, and this at the same time allows to find some other sensitive theories with a purely metric part compatible with the stealth condition. We found that in the non-minimal couplet, the scalar field, we recovered and we found new solution, and these are the results. So when the purely metric part is Einstein Hilbert with cosmological constant in 3 dimensions or in higher dimensions, we recover the first stealth solutions. In new massive gravity, we found new solutions, which are the time-dependent one. Conformal gravity, we couldn't. But here, in Einstein scalar Gauss-Bonnet and in Lovelock gravity, we managed to find these new solutions. And even more, that any big set like black hole is compatible with a non-minimally coupled scalar field. So imagine you have a purely metric theory that predicts this solution, this big set-like solution. This means automatically that you can plug in your action a non-minimally coupled scalar field, you will have a stealth solution. We have found also that the stealth configuration are not only detectable at perturbative level, they are also detectable at thermodynamical level, meaning that the stealth scalar field screens the mass of the black. What are the other questions that motivate some further investigation is to see if the scalar field can screen the electric charge or the angular momentum. Also, that the question comes here after studying the non-minimal coupling is that if this is an intrinsic property of stealth solution, or this is something that depends on the theory, that we were likely to find an R phi squared that allows to solve all the stealth conditions. Finally, we would like to apply this to other kind of coupling, like the non-minimal derivative coupling that has been extensively studied in as a subgroup of Ferdensky theory, where they have found many blocks. We want to see if we can apply this procedure to find some extension to previously known stealth scalar field in this field. And finally, other idea that could be interesting is that maybe there are some black hole solutions that can be scalarized by a stealth configuration. So then it would be nice to find some kind of correlation, thermodynamic correlation between scalarization and the phase space diagrams in the free energy temperature plane. I think that's all. And before I leave, I would like to invite you to Chile to the Third Pacific Summer School. It's given each year in March. I already organized so we can talk about it. You are all invited. We don't have financial support, so if you have your own financial support, it will be great. If I find financial support, of course, I can invite you. We already did the first and the second, and now we will go for the third version in the next month. So you are invited to the other side of the world. You will like it. It's also the same spirit as here, that to find some new collaboration network and to maybe to start new projects. So you are all invited. I think that's all. Thank you very much.
Thank you so much, Christian. Any comments or questions?
I thank you for your answer. So I wanted to know what about ghosts in your solution? Ghosts.
There is no ghost here because this belongs to Ferdensky theory. So you can manage to write it in the Ferdensky form. So Ferdensky instabilities and both. You have more degrees of freedom because you have an scalar field. Yeah, but these are not pathological because this belongs to a subgroup of the Ferdensky gravity.
How can you ensure about this?
You can linearize this. There is a work from Minamitsuji, Chenchi Yoshikawa. So you can linearize the whole Ferdensky theory, and you can analyze from them that you can survey if there is some Laplacian instability or some post instability by choosing the coupling functions. The non-minimal coupling, in particular, belongs to a healthy part of the Ferdensky gravity.
But I speak about the scalar field itself. What can you show? Because it is kinetic term in your Lagrange, right? So this kinetic term must be positive, or otherwise we will have a ghost.
Yeah.
So how can you ensure that your solutions which include the scalar field has no imaginary part?
If you compute the Klein-Gordon field equation for the scalar field, it has the right sign. There is no any sign. And you can see it from the kinetic term as well. It has the right sign. If it will be from the action, if you will have +1 or 2, that will be pathological immediately at first glance. But if you see the field equations, it has the right sign. There's no any problem with that.
We will discuss about this.
But how you can see, for example, at first glance that it will be pathological somehow?
If you can, for example, plot your scalar field, you can see that it is its behavior. is it in a positive pattern or negative pattern?
Uh, it, 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 it,
So in that case, you can
In fact,
just
if the scalar field diverges, you mean?
have the positive pattern or negative pattern.
Pattern,
Yeah, behavior.
behavior.
Yeah. So if you plot your scalar field, then you can show if it has positive or negative one. And for negative ones, this means that you have ghosts.
Yes,
Because you're kinetic there.
yes, yes.
So in that case, you will have to do some thing to remove such ghosts.
It is true if the kinetic term change sign, you can have some instability. This is true,
Yeah,
as you mentioned. Yeah, but this is not, I can assure you that this is not the case. Yeah.
Okay. Yes, right.
So my question is, you said this model has more degrees of freedom. If you start opening up models to have a lot of freedom, then you can start manipulating a model to fit in any type of observation. So how do you know that your model is really fitting it, or is it just the free parameters giving you freedom to fit anything, but not really actually fit?
Yeah, you have freedom in the parameters because you are solving only the left-hand side of your field equation. So your field equation, the left-hand side is telling you this is the restricted geometry. So I think I'll show you in this part. For example, in this part, the stealth is the spatial geometry has these three, A, B, and C. And as you are mentioning, yeah, A, B, and C, what can be anything you want. You can describe a rabbit or a pink elephant if you want with this. It's true. But this is because you are solving only one side of the field equations. If you solve the other side of the field equation, this integration constant, a priori integration constant, is finally find some interpretation. For example, this one is related with the ADS. This one is related with the mass of the black hole. But there is no way to know a priori what is interpretation only by solving one side of the field equation. You will finally find it if you match with the purely metric path. So this can be in other cases. For example, are given by this, which are previously known solutions, and the interpretation becomes clear once you match it. This C parameter, for example, you see here, it's not clear what it is, but when you match it, this is related with the curvature of the baseline, for example.
Okay, so it is free but limited to the certain condition type.
If you embed this in once you find the purely metric part, you will be clear about the interpretation. Before that, you don't know it.
Okay, so let me see if I understood the philosophy. So you have a background solution, and then you take the background metric and other fields and construct or add a new piece on the right-hand side, a new stress energy tensor, depending on the field. You look the background fields, and then that stress energy tensor now vanishes.
Yes.
With a non-trivial configuration. The
Yes.
condition for
Yes.
that quantity to be zero is some non-trivial configuration for the fields that constitute this new stability.
Yes.
Okay, and then you are implementing it with some scalar field, right? But you could consider maybe some non-linear contribution of the original matter fields, and then you can identify some non-linear terms that can produce another solution of this kind, right? Or maybe even coupling fermions instead of a scalar field. Like psi dagger psi, coupled to R.
Okay, so in what you mentioned at the beginning is the standard procedure. So you find the solution, the background solution for your favorite metric theory, and then you plug it in the stress energy tensor part. And then the stress energy tensor part contains a scalar field. The left-hand side is purely metric. The right-hand side contains the scalar field. So from the left-hand side, you find your vacuum solution, then you plug it in the TMNU, and then you pray for having a non-trivial copy. And this is a step. Okay, this is a step. What we're proposing is the opposite. The TMNU is equal to 0. What TMNU? The TMNU given by this guy here is equal to 0, and we will see what kind of geometries are restricted only by this TMNU equal 0. And then we will survey what kind of theories are compatible with the geometries predicted by the TMNU equal 0. So, if your fermion, for example, you have a purely metric theory, and you can have a fermion, and this, the vacuum solution with your fermion, for example, is compatible with a BTZ like black hole, then you can plug on top of your theory these guys here, and you will have a stealth solution.
Okay. So I think we can play a little bit with that, see if we can find some.
This is allows many to create and to find many solutions. There is one problem that is for BTZ like black hole works quite well. But here, for example, you may think that the Schwarzschild black hole is contained here. But the problem is that if you want to extract the limit from here for the Schwarzschild black hole, and then you will say, you can claim that, oh, I found a stealth configuration for the black hole, Schwarzschild black hole. It's not the case because the limit renders the stealth equal constant, which is not a stealth configuration. But if it's BTZ like, any theory with BTZ like is compatible with the stealth. This is one nice one.
Okay, and this is for specific backgrounds, specific background methods, not a general arbitrary background.
Not arbitrary background, no, otherwise it's impossible to solve it. Yeah, we have to restrict some static configuration.
And the same would be applied in cosmologies.
Yes, in fact, some people found. Yes, some people found these guys here with the film element also worked. Yeah.
Okay.
But I don't remember quite well this result, but
You can have
there was no equation of the state because the TMNU is equal 0.
Yeah, but the point is that you can have the same background evolution, but with different perturbations.
Yes, this is something interesting because also at perturbative level, the TMNU is not equal 0. The perturbation of the TMNU is not equal 0. So you are also exposing the stealth. So at perturbative level, of course, you will have different behavior. Yeah, this is a main difference.
Okay. Okay, so let's time Christian again. If you still have energy, we continue. It's an online talk. Okay. Do you mind if we keep using the laptop? Okay. Okay. So our next speaker will be Alana Carolina. Alana, are you there? Are you ready?
Yes, can you hear me?
Yes, we can hear you. Now you can share your screen.
Just a moment.
Okay, well, Alana Carolina is a PhD student from the Federal University of Ceará in Brazil. Very beautiful paper, and see also which are actually part of it.
Just a minute.
You were showing the slide, but now it's appearing.
It's okay?
Yes, it's okay, but let me, don't speak too much. With the sound here is very, maybe you can control it. Yes, you can start whenever you want.
Oh, it's okay. So, good afternoon, everyone. My name is Alana Carolina. I am a PhD student of Universidade Federal of Ceará, and I will present a recently work entitled Equals and Quasi-Normal Modes of Asymmetric Black Bounce This work I did in collaboration with Leandro Alcântara Lessa and my advisor Roberto Vinhais Maluf Cavalcante and the professor Gonzalo Omo. Okay. So the correct description of gravity in strong field scenarios, it is one of the main open questions in physics. And this because in general relativity, we have the appearance of the singularities, which are regions in which we lose completely the notion of predictability of the gravitational theory. And this question has stimulated a good deal of activity in the theoretical physics community and in many diverse fronts. So one of these fronts are black bounces. The first black bounce solution was proposed by Simpson and Wiese in 2019. And essentially, they changed the R coordinate for this expression in the Schwarzschild metric. So with this modification, we have a smoothly interpolation between no singular black holes and wormholes. And after using the Einstein field equations, we found that this metric is supported by a metric content consisting of nonlinear electrodynamics plus a phantom scalar field. So after this proposal, we have a lot of works in black bounces, but always considering these conditions in the components of the metric. So essentially, Leandro and Professor Gonzalo relaxed this condition, and they consider this general spherical line element in which the dynamics of the is governed by the Einstein field equations, and they found that we can have black bounce solutions supported by anisotropic fluids with certain constraints that is satisfied, for example, for nonlinear electrodynamics. So essentially, we impose the condition of minimum to the area function given by these expressions. And the main point is that they found this interesting relation between the area function and the density of this anisotropic fluid. So we can impose the minimal condition, found the density, and consequently the other components of the metric from the Einstein field equations. So the first metric that they found, they consider the area function of the Simpson-Wilson case, but we doesn't have the Simpson-Wilson metric because we have this factor of correction in this component of the metric. So depending on the parameters, we can have a regular black hole, an extreme black hole, or a traversable or a hyperextremal configuration. And the other case, it is a different way, a different function of give this minimal function to the area function. And well, we have these definitions. And the main point is that in this case, this function is defined just to positive values of R. So we have an asymmetric black bounce, different from the other case. And the another component we found from the Einstein field equations. But the main interesting thing in these solutions is that we choose some constant to have the following behavior. We can have, depending of the signal of L0 parameter, we can have a bounded universe in the internal region near from the orange, I'm sorry. And depending on the value of L0, we can have a bounded universe or an unbounded universe, wormhole essentially. And so they have the same asymptotic behavior as the usually Hazen-Nostrom case. So in this asymmetric solution, we have three objects in which have completely different internal structures, but has the same asymptotic behavior. And our main goal in this work is trying to understand if the phenomenology will be sensible to these different internal structures. So In this way, we will, in a first moment, perform scalar perturbations. So, as usual, we will consider a mesolar scalar perturbation governed by the Klein-Gordon equation. And due to spherical symmetry, we assume the standard decomposition in which we obtain this equation that can be written in the same way of Schrödinger equation, and that have in which have this potential effective. So the literature presents a lot of ways of solve this equation, and in this work we will employ 3 methods. So the first method, it is the WKB approximation, in which we essentially impose the boundary conditions that we just have ingoing waves at the horizon and outgoing waves at the asymptotic infinity. And considering these conditions, we can find this relation to the frequency where V0 is the potential at the maximal R0, and the lambda E coefficients depend on the effective potential and its derivative at R0. And the second method, it is the Postele method, in which we approximate the effective potential by this Postele potential. And with this approximation, we can find an analytical solution to the differential equation in terms of the hypergeometric functions and find this analytical result to the frequency. And the third method, it is the time domain, the more general, in which we define the new coordinates and he write the equation of movement and apply the finite difference method to obtain this expression. So as initial data, we will consider a Gaussian wave packet with these initial conditions. And to find the dominant quasi-normal modes, we can perform a fitting of the numerical integration considering this linear expansion and find these coefficients. So now we will analyze a lot of cases. So just to become clear the structure, we will analyze first the symmetric solution with horizon and after without horizon, and following the asymmetric solution with horizon and without horizon. So in the symmetric solution, in the case that we have horizon, we found that we have a standard potential effective when one single barrier, and with a ring down a standard 2. So we found these frequencies from the 3 different methods, and we found a good agreement between these frequencies. But now considering solutions with parameters that leads without a solution without horizon, we found that we have a double barrier as usual to the wormhole case, but in specifically with small values of the A parameter, we found a third barrier, and this third barrier decreases as the value of the A parameter increases. And this third barrier produces a kind of intermediary echo that diminishes as the case that the barrier diminishes. So now changing the process and maintaining the value of the A parameter and varying the value of the hole density, we found that as we increase the density hole, the barriers are more closer of each other, and this produces echoes that are more closely spaced at time and a little bit that are more closely spaced in the time. So now considering the asymmetric case with horizon, so we have the Heisner-Nostrom case and the 2 black balls with different values of L0, one positive and one negative. So considering the 3 solutions with horizons, we found the interesting case that they have essentially the same the same mode of the Hazen-Nostrom case. And this essentially is because in the tortoise coordinate in which the differential equation is defined, we have the same potential effective. And in the tortoise coordinate, we put the horizon, we map the horizons to the less infinite. So in the tortoise coordinate, it is not sensible to this internal structure that they have different of each other. And we can use the three methods to confirm that we have essentially the same frequencies independent of the value of L0 if it's positive or if it is negative. Now considering the case in which we have a bounce with a horizon and a bounce without horizons, the bounce in which have horizon, we have again the same mode as the Hazen-Nostrom case, but the case in which the bounce doesn't have horizon, we have that the ringing down phase will be sensible to this case. Besides, have the same initial condition as expected and the same late time tail as expected too, because they have the same asymptotic behavior. But in the ring down stage, it is sensible in this case without horizon. And now considering that we have the two black balls without horizon, the standard behavior maintains in which we have the same initial condition, the same late time tail, but the ring down phase will be different, will be sensible in this case. And finally, considering the case in which, including the Hazen-Nostrom case, doesn't have horizon, we have essentially the same behavior, the same initial condition, the same late time tail, and the ring down sensible to this internal structure. And when in this case we doesn't have I-COOP, and the potential are regularized in the black bounce case, different from the Hazen-Nostrom case. So when we increase the density, we see that we can have profiles of black bounce case really near from the Hazen-Nostrom case and without equals. So concluding, we have configurations with horizon exhibit a standard ring down waveform, and curiously, in the horizon configurations of the asymmetric solution, the spectrum is independent of the sign of L0. But in concept, horizontal asymmetric solutions exhibit a potential with a rich structure characterized by the appearance of a third central barrier. In particular, we found that the third barrier becomes more pronounced as the parameter A decreases, approaching the classical singular regime, and that the energy density controls the proximity between the potential peaks. And another important outcome, I'm sorry, how can I change it? Another important outcome is the regularity of the effective potential in the asymmetric configurations in the limit in R goes to 0, and the profile of the emitted waves when horizons are present are essentially degenerated and provide no information about the internal structure of the objects, which is natural given the restriction imposed by the causal structure. So some effects begin to be observable when the horizon disappears, showing some generic difference between the Hazen-Nostrom geometry and the regular black bounces. Nonetheless, these effects occur at such low amplitudes. So our finds indicate that there might be scenarios in which the dominant quasi-normal mode frequencies emitted by compact astrophysical objects may not be able to clearly convey relevant information about the inner structure, such as a singularity, a wormhole through, or a bounded universe behind the through. So some references in in particular our material that is available in the archive. And I want to thank you, my group, LASCO, and the Universidade Federal do Ceará and Universidade de Valencia for the structure, and CAPS for the financial support. So I'm sorry about my English, and thank you for your attention.
Thank you so much, Alana. Any comments or questions? I have to say that Alana did part of this work while she was performing a visit in this department. Okay, she has been here for 6 months, or yeah, 6 months. Yes. Okay,
Yes,
so
yes.
Christian, you have.
Thank you, Lara, for your presentation. I don't know if you can hear me. Yes.
Can you
Yes, yes.
hear me?
Yes.
Okay, Christian here. You show a solution at the beginning about a regular black hole. So a regular solution, no curvature, not a singular curvature. So my question is about the action principle behind. Is this solution embedded in some action principle or theory?
I'm sorry, I listened just some parts. And the first solution, yes.
Yeah. So the question is if the solution, if I understood correctly, if the solution that you are presented comes from a variational principle, if you have a theory with some matter that provides these solutions.
And the asymmetrical, the asymmetric, essentially, I'm sorry, this.
Relativity.
But that is isotropic fluid.
Anisotropic.
Yes, yes, an isotropic fluid generates with some constraints in the equations of states. These constraints are satisfied by nonlinear electrodynamics, and this essentially is the source for these equations.
So then the isotropic fluid violates some energy conditions.
I'm sorry.
Yes. She said yes.
Thank you.
Yes, because when you have a throat like a wormhole, you know, the congruences must feel some repulsive effect. So you have repulsive gravity, and this is an indication of violation of the energy conditions. Otherwise, everything would be convergent gravity.
I mean, to remove, also to remove the singularity.
Yes. Okay. Any other comment or question?
Also, I don't know too much about the quasi-normal modes. I'm not that familiar, but so finally, you cannot have an insight from the quasi-normal modes signal about the regularity of the space-time in the origin center. You cannot have access. There's no footprint about the fact that it's regular.
Well, that depends. Well, maybe Alana, you want to mention something? This is claiming that you cannot have information about the interior from the emitted quasi-normal modes. What do you think about this?
I mean, it would be nice. Wishful thinking to say it would be nice to have an instance to say, this is a regular black hole. Not the quasi-normal.
From the quasi-normal mode.
Yes.
Yes, that's the point. That's why she's comparing all these
And at the end,
different solutions.
of
Well, maybe Alana, you can explain if there is any hint from the emissions about the internal structure. I think it's your last conclusion.
yes, no, I was reading that, but I was interested in maybe something else that you can say about the regularity of the black hole from the quasi-normal mode.
Well, the point from here is that even the Reisner nostrum naked singularity provides reasonable quasi-normal modes. So, and that's a naked singularity. So, a naked singularity is well behaved. There is emitting quasi-normal modes with finite frequencies and amplitudes. Then a non-singular object should behave also correctly. It's very unlikely that you get any relevant, a big signature. And the point from this analysis is that in most of the configurations, it is impossible to distinguish.
And close to the horizon, where the horizon may be difficult there.
No. In particular, when you have horizons, you don't see anything from inside because it is causally disconnected. But even without horizons, when you have the black bounces and the naked singularity, it is very difficult to see them. There is some difference, not in this one, without horizons. Can you show the slides beyond slide 16?
16.
Yeah.
16.
Yeah, move forward, maybe to slide 18 or so. A bit more. Yeah, here you can see some differences. You see, this is the black bounce in black and red and rostrum in red, so they are identical with horizons. Okay. And here, one of the solutions, one of the black bounce doesn't have horizons. So it is slightly different. But look at the amplitudes. So experimentally, gravitational wave detectors cannot see anything, not even here. The amplitude is up there. So we will need some very advanced beam detectors to see these bounces and check if there is any difference, or even the time at which the oscillation ceases to transition to the state. So you need a huge sensitivity that there is not there.
So in principle, is detectable.
Technical, yes. With 100% efficiency, it is detectable. The problem is that it doesn't exist. We don't have the technology. Yes. Okay, so any other comment or question? No, if not, then let's thank Ana Carolina again.
Thank you for the opportunity. So can I stop screen? Share? Okay.
Yes, stop sharing, please. Now it's time for last but not least. So today, Salvador Mengual, you use your computer. Yes, sure. It's a matter of disconnecting here.
Now, speak up now.
Hello, can you hear me?
¿Podéis oír ahora? Ok. Sí, funciona.
Okay. Well, I was saying that one of the earliest approaches for solving the equivalence problem is the so-called Cartan-Calhede algorithm, which consists of assigning a frame to the space, an adapted frame to the space-time geometry, and then obtaining the Cartan invariants, which uniquely characterize this space-time geometry locally. Then ideal characterizations appeared as an alternative to the Cartan-Calhede algorithm. Ideal characterizations are a set of tensorial equations whose fulfillment also characterizes locally the spacetime geometry. They are called ideal because they are intrinsic, meaning that these tensorial equations are written in terms only of metric concomitants, which are tensors which can be constructed out of either the metric or its covariant derivatives only. Then deductive, because no extra inference process is needed in the construction. Then explicit, because these metric concomitants need to be given explicitly in terms of the metric tensor and its covariant derivatives. And finally, algorithmic, because this procedure can be put in the form of a flowchart with a finite number of steps. So, well, first of all, this philosophy cannot be employed to algorithmically obtain either quantities or properties intrinsic of this space-time. And we will refer to such procedures as ideal determinations. But now, ideal determinations and characterizations are useful for solving the equivalence problem, for sure, but also in many other fields. For example, for achieving a fully algorithmic characterization of the initial data associated with a given solution to the Einstein equation. Then also in numerical relativity, the near satisfaction of these tensorial equations associated with a given ideal characterization may be indicative of the local proximity of the numerical solution to the space-time geometry associated with the ideal characterization. Then finally, ideal characterizations have also been proposed as a fundamental tool for making gravimetry in relativistic positioning systems. But the aspect we are interested in this case is the fact that their algorithmic nature makes them especially suitable to be implemented in computer algebra programs. So let me talk about computer algebra programs, in particular in general relativity, for general relativity. The complexity of the computations in general relativity was actually one of the key motivations for the early development of computer algebra programs. The term computer algebra actually refers for both the theory and the implementation of computer programs for making these symbolic manipulations, usually in mathematics and calculus. So in general relativity, computer algebra programs were used, for example, for solving the equivalence problem. Actually, Amann was one of the first who implemented the Cartan-Calhede algorithm for solving the equivalence problem in CLASSI, a very old program built on SHIP. But then later on, others implemented the same algorithm in the GR tensor package for Maple. But then another very well-known computer algebra program is Mathematica, which is the one we will focus in this talk, in particular on Exact, which is a package for Mathematica. So let me talk about Exact, efficient tensor computer algebra for the Wolfram language. So as I already said, Exact is a suite of packages for Mathematica. It incorporates tools for both the manipulation of expressions in arbitrary indices, but also the evaluation of components in a given coordinate system and metric. It consists of 4 packages which act as the kernel for all the others: Excova, Extensor, Experm, and Xcore, developed by José María Martín García. Well, and Excova also in collaboration with David Illanes. But then several authors have developed a large number of modules to extend the core functionalities of Exact in several different directions. Here you have some examples. And One of such modules is actually XIdeal, this package that Alfonso García Parrado and myself have developed with the objective of implementing ideal characterizations on Mathematica and in particular on exam. So now let's talk about XIdeal. As I said, the goal of XIdeal is to implement these ideal characterizations and determinations on Mathematica. At the moment, it has implemented 14 functions. You can see here, well, a list with all of them. We have a function that characterizes the Petrov type of a given metric, a perfect fluid question to determine whether a solution is a perfect fluid solution or not, perfect fluid variable, the model perfect fluid Q, etc. As you can see, at the moment, half of the functions are related with perfect fluid solutions because I started developing this package at the same time while I was doing my PhD, which I'm about to finish, and my thesis is about perfect fluid solutions. But since more ideal characterization and determinations continue to appear in the literature, we keep implementing them, and this is a task that somehow still remains open-ended. However, a usable version can already be found on GitHub. So what I will do now is I won't explain these 14 functions, obviously, but I will use some of them as an example to show you, on the one hand side, how they work, and also the philosophy we want to achieve with this program. So let me start with the Schwarzschild characterization. Well, the Schwarzschild characterization was found very long ago, but the ideal characterization of the Schwarzschild metric was found first by John Ferrando and Juan Antonio Saez. Their work was based on the classification of the type D static vacuum solutions by Ehlers and Kuhn. Ehlers and Kuhn classified type D static vacuum solutions in 7 classes: the C metrics, the B 1, 2, and 3 metrics, and the A 1, 2, and 3 metrics. What Ferrando and Saez did was they found an ideal labeling of each of these 7 classes, and therefore they also found an ideal characterization of the Schwarzschild metric. So let's see how it works. First of all, we need to obtain the necessary metric concomitants. And as I said, in order for this to be an ideal characterization, these metric concomitants need to be given explicitly in terms of the metric tensor or its covariant derivatives. And that's what I'm doing here. These are step-by-step what you have to do in order to obtain the necessary metric concomitants. And once you have obtained them, you can follow this algorithm here to ideally classify your static type D vacuum solution in one of these 7 classes. So this algorithm here is implemented on XIdeal. Let's see how it works. First of all, you need to open your Mathematica notebook and load the package XIdeal. This will automatically load all the other necessary packages from Exact that it needs. Then you need to define your manifold, your chart, and the metric that you want to use as the input metric, as the test metric, the one you want to check whether it fulfills whatever condition, in this case, whether it is the Schwarzschild metric or not. Obviously, as you can see, it is the Schwarzschild metric, but this is just a test to see if the program is working. Then also we need to define some assumptions, because in order to check when some ideal conditions are fulfilled or not, these assumptions here are important, in this case, meaning that we are outside the horizon. And finally, we also need to define an arbitrary time-like unitary vector to perform this step here of the algorithm. But an arbitrary one, in this case, for example, the simplest one you can find, actually. So that being done, you give that quantity and the metric as the input to the XIdeal function, static vacuum type classified. And as the output you get that indeed our test metric belongs to the A1 class of metrics, namely it was the Schwarzschild metric as we already knew. So perfect. Up until now, everything is working. Now let me tell you one question.
Yes, one question here.
Sure.
I understand what is a type D metric, but I don't understand the subclasses, how it distinguishes subclasses.
Do you mean the theoretical classification or how they are differentiated here in the algorithm.
How you differentiate there? I mean, how the algorithm said this is symmetric, why this is symmetric and B1, B2, B3?
Actually, I didn't obtain this ideal way of classifying the metric. I only implemented it. But most of these ideal characterizations and classifications, let me go back. First of all, you need to understand what this classification means.
I'm not familiar with this. I mean, I'm familiar with that IV metric, but I'm not familiar with this C, B1, B2.
Right now, like, I don't exactly know the differences.
This is the criteria. These are the criteria. If they satisfy these conditions, then you are in type B. If it doesn't, it's B. If it does, say.
Do they admit some different interpretation? I mean, are there some physical? Because we know that some type of in the Metric classification, certain type of spacetimes classified by the using the Newman-Penrose formulas, for example, admit some interpretation. You can say that this is a PV wave, this is a gravitational wave. This is
actually, we are getting to the Metric classification.
Usually, for example, usually black holes are type D.
Spherical symmetric metric in general.
Yes. What I don't understand is they admit some interpretation. I say that what you gain knowing if this belongs to the C, B, or A. What? If you get some insight, or what is this useful? Is this part?
If I like, I don't know all of them, but if I remember well, for example, the interior Schwarzschild is also an A metric, but with this alpha negative. But somehow Ellis and Kuhn just took all the general metric of a vacuum type D solution and found all the different classes that they got. And if you like simply saying we have this function, so this is either positive or this is negative, or this is positive or this is negative. And then Fernando and Saed, what they did is that classification, they wrote it in terms of explicit concomitance of the metric tensor. So at the moment, I don't exactly know what differentiates each of them. But we can look for it afterwards if you want.
For example, if you put any metric that and you want to check this is equivalent to traction. If an extraterrestrial, an alien comes with a paper with a metric, any metric,
sure,
with all the components on, and maybe this is traction. Can you detect that this is traction in the keys?
That's what this algorithm is telling you. If you obtain this concomitance for which you only need the metric, you build them, you plug them there, and you end up in A1, then that is Schwarzschild. Otherwise, it's not.
I see. I have used Exact and Extensor, and also use other package which is the RGTC package.
I haven't used that one. What's that package for?
It's RGTC. You can compute by components to give the metric and then compute the rich tensor, the byte tensor, everything.
Extensor does that, actually.
Yes, the XCOVA, I think you can.
XCOVA in a particular coordinate system or chart, exactly.
Yes. So in Extensor you have like one set which is purely symbolic, and one set which is by components.
Extensor is purely symbolic, XCOVA.
Yes, yes. RGTC package. Once you switch on other components of diagonal components, it takes a lot of time for computing invariance. Now my question comes here that if this is optimized in order to decrease the time of computation.
I'm still working on that. Es que está aquí.
But it's quite heavy. If you switch on all the components, you put it then and set the computer compute all the curvature invariance, it's quite heavy.
You are getting ahead because that's on the conclusion slide.
Okay, yeah.
Yeah, to answer your question, if the chart in which you are writing your metric is very complex, consider that in the end you will have to check whether this is zero or not. So you will use simplification functions such as simplify, full simplify, or complex expand, or whatever. And that can take a lot of time or an arbitrary amount of time in some cases. I will talk about that later. Thank you very much for the questions. So yeah, I was moving. We already explained that it works for this very simple case. And now I was going to move on to the Petrov-Bell type determination. In case someone doesn't know what this is, when studying the classification of the Weil tensor, you can do so by studying the eigenvalue and eigenvector problem of the endomorphism defined by the self-dual Weil tensor and the space of bivectors. When you do that, you get 6 different classes, which are the Petrov types of a given metric. And you can ideally determine the Petrov type of any metric. Again, the first step consists of obtaining the necessary metric concomitants, which again here, and this is the important step, we give explicitly in terms of the metric tensor. Once the necessary metric concomitants are obtained, you can follow this algorithm here, which again ideally determines the Petrov type of a given metric. So this algorithm is implemented on XIDEAL again, and I will apply it to the same metric as before, the Schwarzschild metric. So the first steps are exactly the same, and now you just give the metric as the input to the XIDEAL function Petrov type. And as the output, you get, as we already knew, that the Schwarzschild metric is of Petrov type D. Now, another quite particular example is the determination of the multiple diagonal directions. So what are these? When you study the relative position between the two null cones defined on the one hand side by the metric on the space of bivectors, and on the other hand by the endomorphism defined by the self-dual Weil tensor, you get that generically they cut on for the Weber null bivector. So the Weber null direction is the fundamental direction of each of such the Weber null bivectors. In particular, Petrov types N3 and 2 admit a single multiple the Weber null direction, which is quadruple, triple, and double, respectively. These are the so-called Bell radiative gravitational fields, and this multiple diagonal direction is the fundamental direction of such gravitational field. So it's quite important because somehow it's a preferred direction in those spacetimes. But then we have that in Petrov type D metrics, they admit 2 double the Weber null directions, while Petrov types 0 and 1 admit no, the Weber null multiple Weber null direction. So, of course, to ideally determine these multiple Weber null directions, the first step is to identify the Petrov type of your metric. Once you've done that, you follow these algorithms here, and you obtain explicitly your explicit expressions of the multiple Weber null directions. Again, this algorithm here is implemented on XIDEAL. We will apply it to the same metric as before, the Schwarzschild metric, which now we know it's of Petrov type D, so we are only interested in that branch of the algorithm. And the first steps are the same as always. Now we also need to define this arbitrary time-like unitary vector and also an arbitrary bivector, but completely arbitrary. So the simplest one in this, like in this case, almost every component 0 and 2, 1 minus 1. We need them to perform this step here of the algorithm. But once we have defined these two quantities, we give them together with the metric as the input to the XIDEAL function, the Weber null directions, and we get the expressions in the coordinate chart that you previously defined of the, in this case, 2 double the Weber null directions of a Petrov type D metric, in particular the Schwarzschild in this case. Now, finally, let me tell you about a functionality that the program also has, which is not an ideal characterization or determination. It's actually a matrix database. By using this function here, exact solution data with no arguments, you get a list with the names of all the metrics that the program has incorporated. This is to allow the user to load metrics, any metric of this list, without having to type it every single time manually. So if you don't write any argument, you get the list with the names of all the metrics that are currently implemented. Now, if you write the name of the metric you want, you get the all the coordinate systems in which it is currently implemented. Now, for example, Svarshield is at the moment implemented in 3 different coordinate charts, while Friedman only in 1. We will continue working on that. So let's stick to Friedman. If you now also write coordinate names, you get the names of the coordinates in which the metric is written in that coordinate chart in particular. You can also get the parameter's name and the scalar function names, and with that information, you can also call this function to load the metric. Obviously, first of all, you need to define the manifold, the coordinate chart, and define the constant symbol and the scalar function by using the name that you got. And then you can either get a matrix whose components are the metric components, or the object in which extensor works, which are the C-tensors, also with the components of in this case, the Friedman metric. Is it possible to see the figure?
No, it's not possible because we had a problem with the camera.
And finally, another thing that can be done in this matrix database is if you write the word classes as in the argument, you get all the classes to which this particular metric, in this case the Friedman metric, belongs. Because we also put a classification, and also if you instead write perfect fluid, you get all the metrics that belong to that class and all the combinations you can think of. Then another functionality that it has is it allows the user to load its own metrics in case we didn't have the time or whatever, or we didn't know some particular metric. The user can also load its own metrics to this database. So this is it for today. As I said, at the moment, XIdeal has implemented 14 functions implementing either ideal classifications or characterizations. But a lot of work is still to be done. For example, it needs a lot of improvements. For example, the first one, to make it more user-friendly and also robust against the use. Then also, I mentioned the assumptions when I was giving the example of the Svarshield metric. In some cases, assumptions are needed to even get any result. In some cases, the result will depend on the assumptions. But in some other cases, the result, to even get a result, you need some assumption. So it would be nice if at least the program could tell the user when extra assumptions are needed. Then the program also needs some additions. First of all, to keep incorporating the ideal characterizations and determinations that can be found in the literature, but also to solve the fact that when you give a metric as the input, XIdeal classification functions will, in general, place it in the most general family to which it belongs. So it would be nice if the program could give the extra conditions that potential subfamilies should fulfill in order to belong to subclasses of this wider class of metrics. That's something that we are working on. Then also keep expanding the matrix database, because as I said, well, I showed you the list. It has incorporated at the moment around 30-something metrics, some of them in different coordinate systems, but there's still a lot of work to be done in that direction. Finally, also the documentation. All of these functions already come with at least some very basic documentation, some of them more complete, some others more basic, but we are still working on completing all these documentation notebooks. And finally, the limitations of the program, which is what you already asked about the computing time. Because indeed, to check when some ideal conditions are fulfilled, the simplification functions are used, just simplify, or full simplify, complex expand. In some cases, some simplification functions are better than others. The user can choose the simplification function that each of these functions uses, but you need to know which one is better in some cases, and in some other cases, none is better than the other. And if your metric is written in a very weird alien coordinate chart, can take a lot of time to simplify the fullest. That is something I still don't know how to completely solve. We have some ideas, but I still don't know how to completely solve that problem. So that's all work for the future. Indeed, there's a lot of work to be done, but under my point of view, this is quite promising. So thank you very much for your attention.
Thank you, Salva, for your talk. Any comments, questions?
Yeah. So there is no procedure or packages that you can use to, for example, I have a system of differential equation, linear differential equation that can your package be able to solve it.
To solve a system of differential equations, but what does that have to do with this?
No.
So if no,
Yeah, well, the exact framework is for manipulation, tensorial manipulations and analysis of metrics and space.
Tensorial expression.
Yeah, in mathematics, you can solve equations.
but generally one cannot solve. And if
Yeah, this is a package that is that analyzes the properties of solutions.
Solutions to the spec to.
so
yeah.
if I have many different solutions for the same system, can your package tell me which one is the physical?
One, which is the physical one.
If you have different solutions to the same,
for the same system.
at the moment, no. I mean, the philosophy of the package is to tell apart solutions to the Einstein equations and only to the Einstein equations.
So all of them are solutions.
Not yet.
Not yet.
So sorry, I interrupted you. Say again.
So all of these solutions are solution to Einstein, for example. Can your package tell me which one of these
That's
is the
very
physical one?
That's very interesting because that's what my PhD thesis is about. My PhD thesis is about studying the physical interpretation of perfect fluid solutions, because we need to focus on something in particular. Perfect fluid solutions to the Einstein equations with spherical symmetry, because otherwise that was too big. So there are some functions that could help you do that, but they don't do it yet automatically.
So
We have functions that tell you whether your solution is a perfect fluid solution. If yes, if that solution is a thermodynamic perfect fluid solution. It can also give you the variables of a perfect fluid solution, if the solution is perfect fluid. There's also a function that tells you if your thermodynamic perfect fluid solution is a generic ideal gas or a classical ideal gas. We are working on a function that would tell you if your solution is a Singe gas, but that's still being worked on. Yeah, exactly.
Yeah. Okay, and yes, is this constrained to 4 dimensions? I mean, if you want to expand the number of metrics in higher dimensions, string theory people have thousands of solutions.
There are already thousands of solutions in 4 dimensions, and we are still working on that. So for now, I would constrain to 4 dimensions. First thing is that I would need the ideal characterization of those solutions, and to do that, you need to really study the solution. Like, in order to obtain the ideal characterization of a single solution, you need to study and really understand what the properties and the geometry of that solution is to then obtain the ideal characterization. And once you've obtain the ideal characterization, implement it.
Mm.
So it's
Okay.
not that easy.
You need a good reason to study
Exactly.
individual method. Okay, very good.
So, at some moment you mentioned that it can, the program can tell you if this is an ideal gas or not.
Yes.
Okay, but this ideal gas in the sense of it has entropy, pressure, volume, equation of states.
Exactly.
and
Well,
if it's same,
first
so
that
you can distinguish if it's a black or not.
last question, I don't know. First of all, a thermodynamic perfect fluid is a perfect fluid solution to the Einstein equations that admits temperature, entropy, and so on with any equation of state. Then an ideal gas is a thermodynamic solution to the Einstein equations whose equation of state is that of an ideal gas. And those things are already implemented.
So maybe we're talking about different setup scenarios. Because there are some, the so-called black hole chemistry, and they promote the cosmological constant to a
Yeah, we're not talking about the same because well, at least a bar shield is a vacuum solution. So that's
yeah,
not
actually yes, it can be interpreted as a it has question of state. It can be interpreted as a van der Waals gas pressure.
But you are thinking about
It's different.
black hole thermodynamics and not perfect fluid.
Exactly.
I got confused.
Thermodynamic fluids.
The thing is that since my thesis is about the thermodynamics of the fluid
No, the
source
fluid
of the Einstein equations, that's the reason why most of the functions which are already implemented are about that. In the future, if I have time and energy, well, obviously we will continue adding functions with characterizations and determinations to the program. But again, the first step is to actually obtain an ideal characterization of whatever you want to characterize.
And the input is always any method that you want.
Yes.
I mean, it's not necessary that this is a solution comes from some X theory. I mean, the problem with the method, the input of the method
Yes.
can be anything. Maybe it's not a solution. I mean, they haven't found the theory in which this solution can be embedded. I think, for example, the Bardic solution. Bardic solution was proposed. The space-time was proposed, the metric first, and then they found the way to embed it in a theoretical framework. So, my question is related to this. Is the input only the metric, or it assumes that?
Only the metric. It's true that for some functions it will work regardless of the theory, but for some others, for example, the perfect fluid characterization, the perfect fluid characterization has been obtained assuming classical general relativity. So in that case, probably you would get an answer which wouldn't make sense, I guess. But for some others, the theory doesn't matter.
Okay, any other question or comment? If not, then
The one that
It's more of just a technical thing. We kind of asked a lot of the same question back when you was in South Africa. Mathematica is paid service. So, like for our university, we don't have access to Mathematica. Why did you go for the Mathematica because of all the other packages? And if you could do it in something like Python that's free, would you do it in that? More good reason.
honest answer is because I learned how to use Exact, and also Exact offers a lot of facilities to work with tensorial equations. Can this be done in other? Well, Maple has already packages which can do similar things. For Python, I don't know. I've never worked on symbolic things with Python.
And also about this package, I think that's quite enough. Maybe here's wrong, but the RGTC package is something that I can show you later. That is quite useful. Also, of course, this package is quite useful as well. I used it in symbolic computation, but in this package RGTC, you can implement the Newman variables formally. You can compute all the invariants, and then you can let's say by scanning the Howard invariants, you can classify according to the better classification.
Yeah, that's completely true. This is just an alternative.
The problem comes when you have some off diagonal terms, because it's quite sensitive to it's quite heavy at some moment. It cannot work anymore. It gets in an infinite loop. And so it is.
What I usually say is that this alternative is not better than the other, or the other is better than this. You just sometimes need alternatives, because in some cases one is better, and in some other cases the other is better. So it's nice to have as many alternatives as possible.
Okay. Thank you so much for your talk, Salva.
Thank you.
Okay, and thank you everyone for this wonderful session, and tomorrow more. Okay. Thank you. Es una pena que no haya ido a ver.
Ya.
Si también han visto. Okay.